All right, this is your 12.3 video, and it's kind of a conceptual video as well as an examples video. 12.3 is talks about power, and so in terms of electricity, remember we already talked about power in a previous chapter in terms of like horsepower for an engine and that sort of thing. This is electric power, and electric power is figured by taking the current in a system, and multiplying times the voltage. So remember, if you have a circuit and you've got current running through that circuit and the voltage of the battery, you can multiply those two together to figure out the power of that circuit. And so you can see that if current gets bigger or voltage gets bigger, then of course that creates more power. So if they both get bigger, that really increases the power. But increasing either one of these, of course, would increase your power. So the main formula that we have for power will be current, which is the letter I, times voltage, which is the letter V. There are two other formulas that you can find for power just by simply doing some substitution, which I won't go through with you, but we can also use voltage squared divided by resistance, or current squared times resistance. Any of those three formulas will calculate power for you. I ran across this neat chart. That's kind of it's called the electrical circle formula, or the formula circle for electricity. And it's pretty cool in that if you want to find power, you look in this quadrant. If you want to find volts, you look here. If you want resistance, you look here. And if you want to find current, you would look here. And so there's three different formulas for each of those. So if you want to find volts, how many volts, and you know power and resistance, then you could use this formula. If you know current and resistance, then you would use Ohm's law, which is this formula. And so on all the way around the circle. So this is really handy. I'll have this for you on the final as well for you to use. The only thing that's not really on this wheel would be the Q. Remember how Q represents a charge, the amount of charge. So if you know charge, this may not be as valuable to you, but we still have that list of formulas that I gave you. And so I've got that's from your 12.1 worksheet you had to do. And I've added power in here to this list with the three power formulas. And remember that we used Q to find electric current. Current is the amount of charge divided by time, and also the work done by a battery is charge times electromotive force. And once again, remember the electromotive force and voltage can be interchangeable for what we are doing. They're a little bit different, but not different to the extent that they don't mean the same thing in what you're doing in these problems. And so electromotive force, voltage, those are going to be interchangeable for us, and the Q stands for current. And so we have that, the circle wheel of formulas, and these as well that we can use for this chapter. All right, so our first example is on page 766 in your book if you want to follow along. It's example 21.8, and it says a handheld electric fan operates on a 3-volt battery. So we know our voltage is 3. If the power generated by the fan is 2.2 watts, and I guess that's another thing I didn't really discuss, is that power is measured in watts. It's really a power is a joule per second. Joule per second. And instead of calling it a joule per second every time, they named this after a famous physicist as well. And so that becomes known as the watt, and that's what like your light bulbs and that sort of thing is measured in. So when they tell you how many watts a light bulb has, that's simply a measurement of power. All right, so in this particular problem, we have 3 volts and a power of 2.2 watts, and they want us to find the current. So we're looking for I, which is current, and we know V and P. So if you go back to your wheel of formulas and go to the current section, remember you know V and P. So go to the wheel. I'm looking for current, which is I, and I know P and V. So I'm going to want to use this formula right here. I is equal to P divided by V. So I will simply need to take 2.2 divided by 3. So dividing that gives us a current of 0.73 amps. All right, next example. This one's on the same page, number 33. It says a flashlight operates with a current of 3 amps and a power of 4.5 watts. What's the voltage? So this time they're giving you current, which is always given in amps. They're giving you power, which is given in watts. And they're asking you to find voltage. All right, so you know you know I and P, and you want to know V. So you go to the wheel, and you find the V section, and you look for I and P. So go to the V section, you look for I and P. It's this formula right here. Voltage is equal to P divided by I. So voltage is equal to P divided by I. So P is 4.5 and I is 3. So 4.5 divided by 3 will be 1.5. So we have 1.5 volts, which is about that of a AA or AAA battery. I can't remember for sure which. I think that's a AA battery is 1.5. All right, so number 34, a 12-volt battery, which is what you would typically hook up to a car, delivers a current of 0.75 amps to start a small gas engine. What is the power produced by the battery? So let me erase this. So number 34, we know voltage is equal to 12 volts, and current, which is the letter I, is 0.75 amps. What is the power? So we are looking for power, and I think I even told you that this one you can go to the wheel if you want to, but I believe that's the formula I gave you to start with. Power is equal to current times voltage, and that's what I know is current and voltage, so I can simply multiply those two together to find out what power is. So if I take 12 times 0.75, you could think about that as simply 3/4 of 12, which is 9. So your power is 9 watts. And that's the answer to number 34. All right, so your next example, if you go on in your book, is on page 768. And so in this one, we even have a picture here for us. It says a battery with an electromotive force of 12 volts is connected to a 570 ohm resistor. How much energy is dissipated in the resistor? How much energy is dissipated in the resistor in 65 seconds? All right, so if you go through what you know, we know electromotive force, which we said is the same thing as potential difference or voltage. They're all interchangeable for these problems. So I know that V is 12 volts. I know I have a resistor that has a resistance of 570 ohms. This takes place over 65 seconds, and we want to know the change in potential energy. And so to do this one, you do have to kind of go back and use the formula that we used for power back earlier in the book, so I'll kind of go through that. Back earlier in the book, when we defined power, we defined it as work divided by time, the amount of work that's done over time. And work, there was two definitions for work. We could use force times distance, or we used change in energy. The change in potential or kinetic energy is also a definition of work. And so there we have another formula for power, change in energy over a period of time. And so I'm trying to figure out the amount of energy. It asks me how much energy is dissipated in the resistor in 65 seconds. So I know time. I know time is 65 seconds. If I could just find power, because I know right now that power is equal to change in energy over time. And if I multiply both sides by a t, then I will know that energy is equal to power times time. Well, I already know time. That was 65 seconds. I need a way to calculate power. Well, let's see. If I want to find power, I need to find power, and I know V and I know R. Remember that this is interchangeable with V. So if I know V and R, and I want to know power. So go back to the wheel. Power section, knowing V and R. Look in the power section, V and R. V and R right here. There's V squared over R. Power is equal to V squared over R. Okay, so I know both of those. I know V is 12. 12 squared is 144. My resistance is 570. So now I just need to type those in the calculator. All right, so if you type this in the calculator to calculate P, you get 0.25. So I know the change in energy, which is what I'm looking for, is 0.25 times the seconds, which was 65 seconds. So 0.25 times 65 seconds comes out to be the amount of energy is 16.4, and remember, energy is always measured in joules. So that is the correct answer, 16.4 joules of energy. All right, next problem is a follow-up problem on that same problem, so we may look back to it, but it says how much energy is dissipated if the resistor of the if the EMF of the battery is increased to 15 volts. So it's basically saying same problem, but what if it's 15 volts instead of 12? So if you think about going back to this problem and doing it with 15 volts instead of 12, we put the 12 right here. So I will just copy this. All right, so now my numbers are going to change. This time my voltage is 15. So 15 squared over R, the resistor. The resistor was 570. And then once I have that, I can plug that back in here. So 15 squared divided by 570. Is equal to 0.39. So I have a power. This is my power right here, 0.39. So I plug that in for power, multiply it times the 65 seconds, and see how much I get. 25 point, let's just round that to a 7. 25.7. So I had with 12 volts, I came up with 16.4 joules, and with 15 volts, I come up with 25.7 joules. So you can see how that increased the energy. All right, next problem is on that same page. Number 36 says a portable CD player operates with a current of 22, we use the letter I, 22 milliamps. So milliamps would be the same thing as 0.022 amps. So remember to convert from milli to just amps, we would want to move this decimal 3 places over. All right, so it has a potential difference of 4.1 volts. So remember, when you see potential difference, voltage, and electromotive force are all interchangeable. So that's 4.1 volts. And it says, what is the power? So I'm looking for power, and I know I and V. Well, that was the original formula I gave you. Power is I times V, current times voltage. And the key thing you want to make sure you do here is convert to amps and don't leave it in milliamps. So multiply those together, and we would have our answer for that. 0.022 times 4.1 is 0.09. So 0.09 watts. All right, number 37, it says the power dissipated in an electric heater is 120 watts. So this time I know power. Let's shrink this up. So there was our first problem. Our second problem, power, is 120 watts. The heater is connected to a 120 volt outlet. So I know voltage is 120 volts. 120 volts, 120 watts. What is the resistance of the heater? So I am looking for resistance, and I know P and V. So I'm going to go to my wheel in the R quadrant and look for a P and a V. All right, so in the R quadrant, I'm looking for a P and a V right here. Resistance is equal to voltage squared divided by power. So I need to take voltage squared divided by power. Okay, so that'd be 120 squared divided by 120. So you can see one of those 120s is going to cancel, and I'm going to have a resistance of 120 ohms. And there you go. All right, next problem. So this problem uses the concept of a kilowatt hour, which is what electricity is measured in as far as an electric meter. Like, for example, your parents, when they pay their electric bill, they pay it based upon the number of kilowatt hours of electricity your household uses. And so how many kilowatt hours you use times the cost charged per kilowatt hour is how your electric bill is figured. And so let's talk a little bit about what a kilowatt hour is. Well, anytime you put a kilo in front of a unit, remember watts. A watt is a unit that we use to measure power. And so a kilowatt, 1 watt, or 1,000 watts. 1,000 watts would equal 1 kilowatt. Just like 1,000 meters equals 1 kilometer, and so on. And so if you think about a kilowatt hour as a unit, anytime you have two units put together like that, that means they've been multiplied. If you remember back to when we first calculated work, we said work was, or a force, it was measured in a Newton meter. And that was because we were taking a Newton times a meter. Or in English units, we call it a foot-pound because you're taking a foot times a pound. So if a kilowatt hour is a unit, that means you're multiplying kilowatts times hours. So as your unit. So if you think in terms of like a 60-watt bulb, if you go to the store and you buy a 60-watt bulb, so that 60-watt bulb would equal 0.06 kilowatts. And if you were to take that 60-watt bulb and put it in a socket and turn it on for 30 minutes. So 30 minutes, if I take my wattage and I multiply it times my time in hours, 30 minutes is half of an hour. So if you take half an hour times 0.06 kilowatts, that would tell you the number of kilowatt hours. So 0.06 times, and I'm just making this up, this is not part of the example here. So that would be 0.03 kilowatt hours. Kilowatt hours. A 60-watt bulb turned on for half an hour means 0.03 kilowatt hours turned on your electric meter. And then that could be multiplied times the cost per kilowatt hour of electricity to figure out how much that light bulb costs to run. And I think in Kansas, I think our average kilowatt per hour is about 12 cents. So I believe they charge you about 12 cents for a per kilowatt hour. Or if you want to write that with a dollar sign, we write it with a dollar sign. it would be 0.12. So if I take 0.03 times 0.12, that's less than a penny. That's 0.0036. So you can see leaving a 60-watt bulb turned on for 30 minutes doesn't seem like much money. But if you imagine keeping that light on for an entire month, that does make a little bit of a difference. So when your parents are telling you to turn off lights, and you think about how many light bulbs you have in your house, if they're all left on solid for a month, that could add up. All right, so back to this problem. All right, it says we have a holiday goose. It's cooked in an electric oven for 4 hours. Assume that the stove draws a current of 20 amps, operates at a voltage of 220 volts, and uses the electric energy that cost 0.85 per kilowatt hour. So this is some pretty cheap electricity here. Similar to Missouri's. I think Missouri's is about 9 cents per kilowatt hour average. Kansas's is more like 12. So imagine that this is a stove in Missouri. How much does it cost to cook your goose? All right, so what do we know? We know time. They're going to cook it for 4 hours. We know the current's 20 amps. We know voltage is 220. And we know the cost per kilowatt hour. So remember, wattage is a unit that's used to measure power. So I need to know how much power this oven is producing in order to figure this out in a kilowatt hour. So if I want to know power and I know I and V, remember that's the first formula I gave you. Power is equal to current times voltage. And I know my current is 20 amps and my voltage is 220 volts. So if I multiply those together, I'm going to get a power of 4,400 watts. So that oven is going to produce 4,400 watts of power, which would be, in terms of kilowatts, 4.4 kilowatts. Simply move your decimal over 3 times, just like we would if we were going from meters to kilometers. All right, so that's the number of kilowatts. The oven's going to be on for 4 hours. So if I take 4.4 kilowatts and I multiply it times 4 hours, that will tell me how many kilowatt hours it takes to keep the oven on for 4 hours. And of course, they don't take into account either how high of a setting the oven's on. That could change things as well. But 4.4 times 4, that is 17.6 kilowatt hours. So if you've ever went and watched an electric meter, your parents have one on their electric pole outside their house, and you can often watch them turn as your house uses the electricity. This one would use, that little meter would measure 17.6 kilowatt hours for using the oven during that 4 hours. So what's it say it costs here? About 9 cents. We'll just round that to 9 cents. And so if you multiply that times 9 cents, that gives you, let's see, 19 point. That gives you $1.58. So $1.58 basically to cook that bird in the oven, which I know doesn't seem like much. It's a small amount, and thank goodness it's a small amount when you think about all the devices that you have plugged into your house. It's a very much a cumulative effect because we have so many things plugged in, and some require more power than others. For example, a dryer takes a lot of energy. So compared to something small that might get plugged into your wall. Anyway, so $1.58 to cook that goose. Remember, in Missouri. All right, next we're going to do number 39, which says the current in a 120 watt or 120 volt reading lamp. So I know current. is 120 volts. And, or I'm sorry, the current can't be volts. The current is 2.6 amps. The current is 2.6 amps. But I do know voltage as well. Voltage is 120 volts. The cost of electricity is 0.075. That's about 8 cents, 7.5 pennies per kilowatt hour. So $0.075 per kilowatt hour is my cost. How much does it cost to operate the lamp for 1 hour? Okay, well, if I want to know the cost, I've got to figure out how many watts of power I have in order to multiply it by my cost. So, I know I and V, and I want to find power. Well, remember, power is equal to current times voltage. Current times voltage, so my power is going to be 2.6 times 120. So if I multiply that together, that will tell me how many watts of power that I have, which would be 312. So this is 312 watts of power. And so if I want to know kilowatt hours, because that's how we measure electricity, I would need to convert this to kilowatts. 312 watts would be the same thing as 0.312 kilowatts. And if I want to know how many kilowatt hours, then I have to multiply that times the number of hours that the unit is turned on, and it says 1 hour. So I multiplied that by 1, and so I have 0.312 kilowatt hours of electricity being used. That's how much the meter would turn. And then you take that and multiply times the price per kilowatt, 0.075, which is a very low cost for electricity. 0.312 times 0.075 gives us 0.0234. So about 2 cents. Take you about 2 cents to run that for 1 hour. All right, so that's all the examples we're going to do for lesson 12.3. I think that'll be enough to get you through the problems. Your problems are posted in Schoology.